firstly, my name is Han. In case you don't know me, I'm now the PhD candidate in the Department of Electric Energy in NTU. So my topic is relevant to the power quality disturbance. Sorry? Yes, this here. Okay. So I will kind of share it now. The teams. Wait a minute. I need to. Yes, to join. Yes. Wait a minute. Turn off. Yes, and share my screen. And also need to share my screen, right? So my topic is relevant to the advanced power quality disturbance classification with the use of the signal processing and deep learning techniques. So firstly, so my today's presentation, how can I just yes, okay. So my today's presentation will kind of cover some different aspects. Firstly, I'd like to give a brief introduction of myself, and then just kind of introduce today's objectives, and as well as some definition, challenges, and the sort of current power quality monitoring research. Then we will have like a 10-minute break. After the break, I will kind of dive into some methods part, including the signal processing and the deep learning. So firstly, about myself, now I'm the third year PhD candidate in NTU. So over the last 2 years, I'm working on the signal processing algorithms and also the deep learning method for the power quality monitoring. And my research topic is about the power quality monitoring in electric grid integrating offshore wind energy. And I have a really amazing like supervisors. And actually last week I just traveled to Lisbon to just work with my co-supervisors in this semester. So it's really nice to just work with them over the last 2 years. And so today, firstly, I'd like to just give you some basic idea of the power quality monitoring, especially in the case of the grid-connected offshore wind energy system. And then I hope you can get maybe some understanding of the feature extraction method for identifying this kind of disturbance signals. And then the last part is to show some advanced versions of deep learning principles especially for the 1D multiple label classification, and also including some results, some applications in the classification task. So when we are talking about the power quality monitoring, the first question is also relevant to the definition. So what is the power quality disturbance? It's a really kind of confusing question because in the different research field, this kind of definition can be really diverse. So in our research, we kind of use the definition from the IEEE standard. So it says the term power quality contains a diverse range of the electromagnetic phenomena that exhibits voltage and current characteristics at a certain time and a location within the electric power system. So the term power quality refers to how well the voltage and the current meet the expected standard for stable and reliable operation. And also it can be really vary depending on when and where it's being measured within the power system. Such as maybe it's near the factory or it's like during some certain peak usage period. So essentially, it is about how clean and how consistent the power is. Besides, we also notice that in this definition, here it's like a statement, it said a wide, let's say, a range of electromagnetic phenomena. So what does it really mean? Here I show some examples. A kind of refers to the different disturbance signals. Here, I kind of list of the flicker, swell, sag, interruption, harmonics, and the transient. So actually, it just like reference to the fluctuations and the deviations from rated frequency, from rated amplitude in the wind farm. So then the second question is that, so why? So now we already know what does this power quality mean, so, but why is important? I'm not sure if you have heard some events that really caused by the power quality, but here I would try to show an example. Is the blackout in Italy of more than maybe 20 years ago. And actually this event was caused by the power quality issues. And you can see it's a really serious event that all of the regions of Italy get affected, and in some regions even they kind of experience like more than 10 hours. Like in this figure, they said it's a 16 hours outage. So actually, this event was kind of caused by some operational issues. So at that time, Italy was kind of heavily depending on some power imports from their neighbor countries like Switzerland, like France. So at that day, a transmission line in Switzerland was damaged by the strong winds, unfortunately, and causing a short circuit when a train branch struck the line. But the problem is that the operators in the Swiss control room was not really aware this urgency. So then, we kind of see this like outage, and it kind of affect about 15.7 million people, and also finally it results in a really significant economic loss. So this insistence highlights the critical importance of the power quality measurement, and that's why here is like really let's say, a need to establish a robust and adaptive strategies for monitoring these disturbances. And nowadays, we can also see there's like it's a trend to integrate some offshore wind into the electric grid. Here, I also need to thank you, Agrippina, for give this really nice introduction of the offshore wind. So this kind of integration provides remarkable opportunities in terms of the stability. Environmental. Just in terms of some cost efficiency. But at the same time, we also kind of see there are some more challenges regarding the power quality issues. They kind of caused by very variable operational events, and also, for example, some power electronic devices used in the wind turbines. So we want to establish a real-time and also really efficient power quality monitoring framework in a timely manner to kind of reduce the final maintenance cost. And what does power quality monitoring really means? Here, I kind of show a typical procedure. Of course, it's like kind of a traditional method, and I will kind of introduce some more advanced framework later. So in this framework, you can see it kind of involves some several steps. The first unit is the segmentation. So in this unit, the event data set is reduced so that the relevant types of the disturbance can be extracted. And also in this unit, we also do some normalization to make sure the different magnitude values can be converted in a scale, it as the per unit. So the second unit is the feature extraction. So in this stage, it kind of includes some certain signal processing algorithm depending on our strategies. After this method, after this unit, actually in some paper, they also use some selection and optimization strategies to select the best or the most optimal features for the following classification. And then the classifier applied on the select feature set, and then finally the decision is made by the final, for the types of disturbance. And actually in this figure, we can also see this like additional processing. So actually this block is used for the activation of the recording instrument. And in our today's presentation, we kind of focus on these two parts, the feature extraction and the classification. So how this power quality monitoring can be used in the real application. Here, I also show there are some three maybe common equipment that can monitor, and also we can see can collect the different types of disturbances. The first one is the PQ analyzers. So this device can really measure and record the voltage, the frequency, and some other parameters. And it's also often used for continuous monitoring of the power quality. The second example is the smart meters. So in addition to measuring the energy consumption, this kind of smart meters, they can also monitor the different indicators, and they are the basis for distributed power quality monitoring and capable of cover a large maybe numbers of users and load nodes. The last examples is the monitoring relays. So in this kind of devices, they kind of have some models can really automatically control the cutoff device, or let's say activate the protection devices. And so after getting some basic idea of the power quality, here we kind of show some four different aspects of the power quality monitoring. So firstly, when we kind of try to implement algorithm, the first step is also to think about the measurements. So in the traditional method, we kind of use this PMU method, which is a really high fidelity data, but it also kind of have show some limitation we can discuss later. And the second part is the power quality events. It's also really annoying because in different papers, they kind of discuss some really diverse range of the disturbances. So what are the events that really matters in our research, really matters to the electric integrating offshore wind energy? It's also kind of really important question to be answered. The third part is the algorithm part. As already shows in the previous procedure, they kind of use maybe some predefined threshold, use some mathematical models to do this feature selection and the classification. Is there some more advanced technique can provide better performance? We will answer later. And the last aspect is relevant to the evaluation metrics, because nowadays in the most papers, they kind of just like consider to use the accuracy as the only one indicator to evaluate the performance, which is of course not really enough. So let's start with the measurement part, the phasor measurement units. So actually, you can see from this figure, it shows the process of getting the frequency and the phasor information. So from this procedure, we can see the phasors from PMU, they are not really authentic, because in the red box here, we can see it's not really directly measured, but estimated during this period. So this processing involves various windowing, filtering, and estimation algorithms, which can lead to inaccuracy of the feature measurements. In some cases, for example, if we kind of see some transient events in the system, this kind of PMU estimate process will kind of cause some errors, and it's not the ideal stuff we like to see. So if there's some better measurements can provide really authentic and really accurate measurements instead of like using some estimation. Here, luckily, we have this choice. so the devices that can record authentic waveform with the precision time steps are becoming widely available today. So here it's like some devices. They are called the synchronized synchro wave measurement unit (SMU), and in using this equipment, they are able to provide like a real, let's say real waveform, and also with really nice time steps, which means that firstly we can really get more accurate data from this unit. And the second advantage is that they can really maybe try to collect and even do some coordinated analysis with the data from different locations with the power system. So luckily, we have some a new method try to manage to get this, let's say, new measurements. So the most common method to get this synchronized waveform measurement is to use the GPS. So because it's like one of the most efficient way to get this like time steps to make it synchronized. But here, I like to say that the term synchronized waveform measurement or the synchro wave measurement unit, SMU, doesn't imply a new types of measurement devices, but rather refers to devices with just a synchro wave measurement abilities. And in this figure, we kind of outlines the benefits of synchronized waveform measurement for the different power quality events. And the different events, they are kind of highlighted in the different colors, the green, yellow, and the red. So the green ones, the harmonics and transients, means that they are kind of get the most benefits from this synchronized waveform measurements due to the time synchronization and authentic waveform of the synchronized waveform measurements. And yes, but there's still some, let's say, challenges regarding this really emerging measurement because adoption of SWM is still kind of in its infancy. And it's due to its really strict time synchronization requirements. For example, there are some challenges regarding the communication standards and also regarding some let's say, database capacities and also decentralized analysis, and it cannot be served in the future work. And to mine information from monitoring results, the root causes of different disturbances should be analysis. So here we show this figure to mention the typical PQ issues and their causes in the wind energy generation parts, the offshore parts, and also in the electric grid parts, the onshore parts. So in our research, we kind of focus on these 6 disturbances: the flicker, transient, sag, swell, interruption, and the harmonics. So regarding the PQ events, we also kind of see some limitations or some challenges. The first one is regarding the updated PQ index, because previously we kind of only consider, as I said, some fluctuations, some deviations in the waveform of voltage, of currents. But nowadays, since we are kind of integrate our electric grid into the offshore wind, it's not enough anymore. So in some paper, they kind of introduce some new definition. It's called energy quality. So which kind of includes some more indicators such as the energy spectrum, average power level, and total power distortion, and some other stuff like standard power deviations. So why they kind of use some new definition? Because they kind of observe in some results, maybe they kind of have this some events in the system. When you are looking at the waveform of the voltage of the current, it's really perfect. But actually, it doesn't mean it's also perfect in the terms of energy part. And the other another challenges is regarding the DC system, because in nowadays the DC system they are really get remarkable attention due to some advantages compared with the AC. For example, the HVDC is already widely used in the current power system. But still, there is some relevant research regarding the power quality events in the DC still kind of in its infancy, still kind of really a field of research really focus on that. So in the future, this part, the DC part, is also kind of really promising research trend and can be kind of get a further analysis. Yeah. And regarding the algorithm part, I previously showed a simple procedure, and by this one, it's like a more detailed procedure to show the whole process. So in the traditional PQ monitoring procedure, the disturbance detection, feature selection, and disturbance classification, they are like three key components. So the feature extraction aim to really extract the patterns and characteristics from the signal through some advanced signal processing for subsequent disturbance analysis or knowledge acquisition. And then after some selection, after some optimization, the classification phase provides, let's say, meaningful information for understanding the nature of the PQ events and enabling appropriate actions and interventions to be taken. So in this procedure, in this figure, you can clearly see they use some like the predefined threshold and also use some selection, let's say, method. They are mainly based on the human being experience. So which means that using this algorithm, maybe we can get really nice performance, but it's not really beneficial for the automatic power quality monitoring. So we want to use the deep learning models to kind of improve this issue, to tackle this issue. And besides, also some challenges regarding, for example, the noise tolerance, the real-time issues, and also the generalization abilities, which also kind of served maybe using the deep learning method. So when we are talking about deep learning, it reminds me of some of my really kind of funny experience, because I remember once I talked with my friend. She's also a PhD candidate, but in the different research field, the chemical engineering. So once we are talking about our like research field, she was really confused about like what is the deep learning. And then I tried to explain. I said like, oh, we just kind of build some framework, and you just input the data you have, and this framework will automatically kind of calculate the results. And but once she kind of get this answer, she was also really confused. Like, but it's the same as the traditional method, because in these two like strategies, we always need to just like write the code, right? And also last week, I just finished my evaluation, and the first question I got from my committee was also relevant to the deep learning, like why you are using the deep learning in your research. So I think it's very important to clarify the idea of the deep learning. So here I show there's like a figure to compare the definition of the AI, of the machine learning and the deep learning. So we can see that the AI is like an overall field of creating machine that can perform different tasks, and whatever through some learning or through some pre-programmed rules. And the machine learning is kind of a subset of deep learning that focuses on learning from data without being programmed for each specific task. And the idea of the machine learning is that the system improves its performance with experience, or it processes more data. And compared with the machine learning, deep learning is the further subset. So it uses some deep neural networks that can automatically learn from large amount of data. So actually, it's like a really significant difference between the machine learning and the deep learning is about the size of the data set. So when we are using the deep learning, it means that we are able to extract more and better features from, like say, maybe a bigger size of data set. And I believe that there are some PhD candidates, they are more professional regarding the deep learning compared to me. So maybe you can hear like more, like better like insight from them in the subsequent license, the courses. And so when we are using deep learning in the power quality monitoring, the first option, the first choice is always the convolutional neural network, which is a really powerful and useful and also typical deep learning framework in recent years. So actually, they has like two different research trends, as you can see in this examples. They kind of firstly, the first trend is to use the 1D signals to do this classification task. And the second trend is to kind of convert the signal into the 2D image using maybe some different signal processing technique, some different transformation technique. So in the first trend, they kind of treat the 1D sampling sequences directly as the input to the CNN models. And in the 2D, let's say when they are using the 2D image, they kind of maybe just incorporate some spatial aware transformations to perform the relevant task. And so we can see there's like differences in the step 1 in the data input, and another difference is in the step 2. We can see like we kind of use some different filters like to kind of contact this performance. And also, I would like to kind of introduce a little bit about the basic idea of CNN. So in these examples, you can see like in the step 2, they kind of involve some different layers. So the basic layer is the convolutional layers, because in this like CNN, we use the convolutional computation to extract different features. And besides these convolutional layers, we have this also pooling layers just followed by the convolutional layers. They kind of try to reduce the spatial dimensions of the feature maps. And also let's say try to highlight essential information. And after that, it's the BN layer, it's the batch normalization. And they just as its name, they kind of do some normalization, try to normalize the input and mitigate overfitting issues, leading to more stable training process. And then in the step 3, it's the FC layer. It's called fully connected layer. And in some paper, they also known as the dense layer. So it's used to facilitate the transformation of the feature space. The finally softmax layer, it actually it's like a normalization function to calculate and output the distribution class with the highest probability score, the probability value. And actually, it's really interesting because from these examples, when we are using the softmax, it means that we kind of regard this task as the multi-class classification. But during this process, they kind of regard the different disturbances as a really, let's say, separate task, and they don't really consider the relationship between different disturbances. So in our research, we also kind of further discuss if we can kind of combine, kind of think about the relationship between these different disturbances. So in our research, actually, we kind of used the multi-label classification instead of the multi-class classification. And also here it's only like a really basic idea of the CNN models, but nowadays we also can see some more advanced versions of CNN. For example, like some RESTnet, some DenseNet, MobileNet, we will also kind of introduce later in my presentation. And also, even just with the use of the deep learning models, we also see there are some challenges. The first challenge is regarding, as I said, the data labeling. We kind of try to use the multi-label classification instead of the multi-class classification to deal with this issue. And another limitation is regard that the event of forecasting, because now we see that we like to extract features, we like to classify the features in real time, but is it possible to also kind of predict this event in advance? As we all know that now we are kind of using some offshore wind and maybe some events that are really affected by the different weathers. So once we kind of get this like weather, let's say, information in advance, maybe it's also kind of beneficial to predict the relevant events. So it's also kind of interesting if we have time to consider this issue in the future. So to provide a deeper understanding of the real-time status of the grid integrating offshore wind energy, the comprehensive assessment is highly beneficial for both the algorithm validation part and also the later problem-solving stage. So firstly, in this procedure, we can see that after the synchronized waveform measurements are getted from this system, then we are using some feature extraction scheme with some signal processing technique to enrich the disturbance details. And then it's followed by a model of the disturbance classification, where the deep learning models are used. Here you can see besides CNN, also there are some other, let's say, versions of disturbance of deep learning can be used, like RNN, like ResNet, and also even some other, let's say, models. And after this part, the evaluation metrics can be identified at different levels, including end-to-end PQ event detect and classification performance, and also the ongoing PQ status of the target power system. So after standardizing the evaluation metrics, it's really necessary to understand the disturbance detection and the classification result for the subsequent decision-making stage. And I guess now I just finished the first part of my presentation. And here, this figure just provide a summary of the first part. And you can see, like, we already introduced the different challenges and the futuristic trend into the different aspects. And for the part 2, I will be kind of more focused on some algorithms. And if you agree, maybe now we can have like a 10 minutes break. And we will continue the presentation maybe on 12:10. Okay. Yes, I just muted my microphone. If you have any questions, just feel free to fire away.
Thanks, Han, for your great presentation. I have two quick questions.
Yes.
First one is, I got curious about power quality measuring with smart meters. Do you have any idea like what common types of power quality issues might be able to measure with the smart meters or already able to measure today, and which maybe not?
Yes, let's back to this slides. Yes, actually, like actually in my research field, I'm more focused on the PMU, the data from PMU, because it's a high fidelity. But from some measurement, from some less papers, they kind of introduced the introduction of the smart meters. And from these papers, they say that there are like various range of measurements we can get from the smart meter. For example, the frequency, the voltage, and also maybe some power factors and some relevant indicators. And so one, for example, if we are kind of like to do this monitoring stuff for the, let's say for the users, for some residential user, for example, maybe the smart meters can be really beneficial, like because it's really like easy to implement. And but for the research, maybe itself, it's more common to use the PMU, because we kind of able to use like more advanced measurements with the data from PMU. So as far as I know, that there's not like a really difference between, I mean, the application between the smart meters and the PMU in real time, because they kind of basically get the more or less the same measurement, just maybe with the different resolution. And so, yes.
So you mean that also the pipeline you presented with neural network classification might be applied to all the different monitoring equipments, or is maybe even already
I guess it's very hard to implement the deep learning into this smart meter, because in smart meter, we are not able to get enough to get, let's say, maybe 10,000 like data from the smart meters. But if we cannot just use some like traditional method, for example, maybe just some typical AI method, maybe the smart meter can can really, let's say, used in this scenario. Yes.
Thank you.
Hello.
Did you benchmark the results of your, let's say, classifiers with more traditional classifiers like
Yes,
there are?
yes, I will kind of introduce later.
Okay.
Maybe like in the second part, because they will kind of more, let's say, dive into the method part. Yeah, but I guess I would not just introduce some, some performance compared to the traditional method. Maybe it's more relevant to the advanced, let's say, method. But I will show there are some tables and features. Figures. Yeah.
Thank you for the presentation. So I was a bit curious on if you know an order of magnitude on how much, for example, this the power quality could degrade of the assets or affect. How much does it imply in terms of more maintenance, reliability study, for quality categories? How this would affect the grid, or is it more empirical studies just with this blackout that you showed in Italy?
Firstly, thank you for your question, but I didn't really hear well because of that microphone. It's like kind of it's a kind of just kind of repeat the questions.
Yes.
Because I didn't really hear well.
Basically, I was curious on, for example, is there any, for example, correlation into how much this power quality has affected one specific grid, or we only have data from outages or blackouts? So is there any estimation of how much, for example, maintenance cost extra or we have associated to that? Thank you.
Yes, like firstly, like we come back to this slide, not this one. Yeah, this one. So actually, like there, you can see like some events like flickers, like transient, like flickers, like harmonics. These two events can get affected by both the offshore part and also the onshore part. So I'm not sure, I would not say like the blackout is very common nowadays. And also from the examples I show, like it's the story of Italy, you can see that actually that time, the operators already see this problem, but just made some wrong like decisions. So once we kind of talking about this like blackout, it's also relevant to the operators themselves. So, and I guess like previously, I managed to get some real wind farm data from WO, from Siemens Gamesa, and also I really see the real, let's say, occurrence in the wind farm. And I would not say it's very common nowadays. Maybe in some cases, in some wind farm, they also did this kind of stuff only happen maybe once each month, but it's just some small, let's say, disturbances like some fluctuation, like sag and spill. And once there's some like outage, maybe it's like a really serious events, and we can just see this events on the newspapers and social let's say media, for example. Yeah, but maybe like let's say maybe more than 2 years ago or 20 years ago, maybe that time was kind of more common. When I kind of Google this kind of events, besides this Italian blackout, I also see there are some lot of events like happens in the same year. So actually that year maybe like several less blackouts in the world, but nowadays it's not, let's say, common like anymore, because we have more advanced algorithms and we have, let's say, better operational let's say strategies. So I would just say that like our research is to try to do some monitoring to prevent this stuff. And it's really lucky that nowadays, like we don't really see this, let's say, events happening like really frequently. Yes.
Yeah, thank you very much. No, it's because apart from these events, I would expect also that these power quality issues would affect the reliability continuously. So you would have to more associated operational costs, or the life of the assets would go down. But also this is related to Conrad's research. But yeah, thank you very much.
Thank you. Yeah.
Hi,
if there's no more question, we can get a break. In the previous presentation, I kind of introduced the challenges of the power quality monitoring, and also here is some some research trend of the different aspects. So for the following slides, they will kind of more focus on algorithm part. So we'll kind of introduce some signal processing method, and also the deep learning models can be used for the disturbance classification. So one, we are talking about the feature extraction. Actually, as I said, it's a pressing need to develop automatic feature extraction method to detect the disturbances in a timely manner. So in the power quality, in the feature extraction scheme, actually they have like two different research trends. The first one is to use some spectral analysis method. This method, maybe there are some really, let's say, famous method like FFT as the STFT. In case maybe you don't know, it's like a short-term Fourier transform. There are lots of let's say analysis in this like spectral analysis research trend. Another trend is called the mode decomposition. And so using these two trends, we are able to get like different types of the disturbance features. And here I would like to introduce like two really typical methods. The first one is the Stockwell transform, and the other one is the variational mode decomposition. So they are kind of working in the two different research trends respectively. So our aim when we are kind of using this feature extraction is to support the operators in better predicting potential faults and making some like better, let's say, maintenance decisions by delivering meaningful features from the disturbances signals. So here, actually, I'm not really, let's say, into some equations because it's really hard to follow immediately. Just show some basic ideas. So for the Stockwell transform, actually, it kind of combined the advantages of two really typical, let's say, technique. So it kind of combined the Fourier transform and also the wavelet transform. So this method, it works in the time frequency domains, which means that with a really, let's say, complicated Gaussian window, it's able to kind of get let's say, get the different frequency components with the time localization. So from these results, we can see here for the different types of disturbances, they kind of show some different figures with different characteristics. And here I'd like to mention that in this figure, in this method, actually before we use that, we need to predefine the number of the frequency bins, which means that the frequency resolution in the result is based on our human being experience or based on some predefined, like say, sightings. And how it can be used in the real, let's say, application. Here I show it's like an example from transaction papers. And in this figure, they said it's MKS. Actually, this MKS is just like a modification based on the Stockwell transform. But the idea is like more or less the same. So within this figure, you can see that like they kind of do this like transformation to convert the signal from time domain into the frequency domain, and then get the image and use them as the input into the deep learning models. And finally, after some different layers, some different models, we can get the labels and the class of the different image. And another one, as I said, it's the VMD. So they kind of working on some different, let's say, domains. I mean that during this like method, they also kind of use some, let's say, transformation stuff. But the signals we finally get is in the time domain. So in this, let's say, VMD, they use some optimization method to try to extract the signals into some sub signals. We kind of set some different modes, and different modes, they kind of refer to the different characteristics, refers to the different patterns of the disturbances. And each models, they are also have their own central frequency. So from this signal, actually, they also have their some predefined settings. So you can see here, for example, the number of the mode is set to 5. So this one is also based on the human being experience, and also it can cause some problems. I will show some results later. And here it's like a figure of how the VMD can be used into the deep learning models. So from this figure, you can see, so firstly, they kind of do this like downsampling and decide the number of the mode. And after some optimization process, they kind of extract different parts, different components of the signal and use them as the input of the later deep learning models. So we can see there's lots of benefits from these two types of the feature extraction method. But at the same time, we also see some limitation. The first one, it's just as that in these two both methods, they always have some parameters. They are predefined. So it's not like, say, a really adaptive method. So it's really totally based on our human being experience and some our knowledge. And so it's not the stuff we like to do, we want to achieve for the automatic power quality monitoring process. Another issue is regarding the really heavy computational cost and also limited noise tolerance from the traditional method. So is there some better way to develop more robust and data-driven feature extraction scheme? So we finally get answer. So here I like to really grateful for Professor Massimo, because like a few months ago, we kind of have a talk in Vienna, and that time he kind of introduced this FIF for the feature extraction scheme. So after I back to NTU, I kind of try to use this method, and it's a really new method, just published maybe in 2020. So 4 years ago. So I'd like to thank you for this like inspiration. And so to resolve the previous issues I mentioned, we can use this FIF to really achieve the data-driven feature extraction, because in this method, they use, for example, some convolutional stuff to really adaptively computed the different, the characteristics, and also the FFT is embedded in this method to kind of speed up the whole process. So with this new really emerging method, we are able to achieve maybe better performance, even with the noisy issues, let's say, signals. And so before we evaluate the performance, it's also really to do some simulation of how we can really generate this power system, power quality events in the real scenario, in the actual application. So here I use an example. It's based on an example in the Simulink. And using this system, we can see that the wind farm is connected to the grid, and we also try to add some different components, add some different events to generate the relevant events. And this figure shows the results using the FIF. So it including the results of flicker, swell, sag, interruption, harmonics, and the transient. So from the figure A to C, you can see that the results can mainly seen in the maybe first component, for example, and it means that these components, they are really just exist in the higher frequency components. That's this event. But for the results of interruption, it's more messy. Actually, it can reflect the really, let's say sudden change of the nature of this interruption event. And for the harmonics and transient, their results is super clear, and which also kind of reflect their, let's say, the characteristics of the simple structure of these two, let's say, disturbances. And then we kind of compare the performance of different methods. And so in these two examples, we can just start from the left one. So here it's the signal with the flicker and sag under SNR, the signal to noise ratio of 50 dB. So we can see it's like kind of a clean signal. And you can see that the result of ST is really perfect. Like we can see that the sag and flicker can really, let's say, reflected in the result. And but the result of the VMD, we can see there are some issues. So firstly, it's not really correct to extract the flicker. You can see just compare with the result of FF, the flicker is not super clear. And when we further check the first one epoch results, we can also see there's like something like mode splitting issues. So actually this issue is mainly due to the predefined modes, because like in the VMD, the number of the mode are like decided by the human being. So once we kind of set some wrong numbers of mode, then they will always have this mode splitting or mode let's say mixing, for example. And to further do some analysis on the more noisy events and with more complicated disturbances, we have this result of this like right figure. And in this figure, we kind of consider the triple occurrence of the disturbances, including sag, harmonic, transient, and the SNR is like 20 dB. So it's like more noisy and more, let's say, actual scenario. And now we found like there's some issue regarding the ST results. So it's overwhelmed by the noise, and we can't see like even one maybe characteristics. And so which means that maybe the noise tolerance can be further improved of this Stockwell transform. And for the result of BND, it's like similar to the previous one. Like they still have there are some like feature, I mean, the mode splitting stuff, like the characteristics of different disturbances are not very correctly reflected in the figure. So then let's just continue to the following deep learning model. And here is it's just as I said, there are some like traditional, like some introduction of the CNN. And but nowadays we already have some new, more advanced version of CNN. So can we really do some evaluation on the more advanced models instead of the basic CNN? So then we kind of discuss some, let's say, some performance of let's say, ResNet, MobileNet, and DenseNet. So use these three advanced versions as the examples. So because in our, like say, the papers, there's like no paper really dive into the advanced versions of deep learning. So we hope to really, let's say, work on that and investigate their, let's say, effective, let's say, the different performance, especially their suitability on the different PQ events. At the same time, also kind of consider to develop the 1D models of this deep learning, because like in the traditional method, they always use the 2D deep learning models. It's good, but still there are some limitations. Firstly, is that when we kind of use these 2D models with, I mean, for the disturbance signals, there are always some data mismatch issues, because these models, they are kind of developed for 2D, but the data we have is 1D. And another, let's say, advantage to use 1D instead of 2D is that if we are kind of manage to develop the 1D models, then these signals, they are really, let's say, investigated directly from the models, and they kind of can reserve, they kind of still maintain the previous order or original characteristics, or let's say the meaningful information from the disturbance signals. And then also just introduce the previous, we also like to use the multi-label approaches instead of the multi-class classification, try to combine the characteristics of different disturbances and to further introduce the relationships between the different PQ events, because in some cases, the different events, they can occur at the same time due to some root causes. And here is an example like how the 1D CNN can be used to extract the features. And you can see that like if you have any interest, you can also just further look at into these papers and say that like in this paper, they kind of introduce this 1D CNN, and from the results also this shows like better and more detailed features compared with the 2D result. And so firstly, let's start with the ResNet architecture. So this figure is the 1D models we develop in our research. So actually, it's a really popular, let's say, deep learning models because it allows deeper stacking with skip connection. So this skip connection is the like special characteristics and the key idea of the ResNet, which means that they have this like shortcut like step in their, let's say, the convolutional models. And you can see that from these figures, the convolution and the identify block represent the main components of the ResNet structure. And the convolutional block, it's used to learn new features where the inputs go through a set of the convolutional layers, the BN layers, and the activation layers, followed by a shortcut connection. And this skip connection typically involves a convolutional layer and a BN layer. You can see here. Here is the convolutional block. And it's very beneficial for mitigating the vanishing gradient issue. And on the other hand, the identify blocks is designed to preserve the learned features within the raw input dimension. So it's similar to the convolution block, but lacks additional convolution in the shortcut path. So there are differences just like related to this like shortcut path. And then here is an example of the mobile net architecture. It's a kind of developed by the Google of like say 6-7 years ago. And the design of this model is to try to have a really lightweight models can really benefit for the real-time issues. So in this, let's say, models, they kind of use two really key steps. The first one is the depth-wise convolution, and the second one is the point-wise convolution. So using these two models, they kind of try to just reduce the computational cost compared with the traditional convolutional steps. And the third example is the DenseNet architecture. So here they also have a like different purpose. The purpose of this architecture is to make the size of the model maybe be minimized. So kind of similar to the ResNet because they also kind of include some like shortcuts connection. But in this case, they kind of use that this connection, it can, for example, here, they kind of get information from all the previous layers. So which means they kind of, even though they are really, let's say, really tightly connected, but the computational cost will be kind of higher than the ResNet. And yeah, and also they have these two different like two key blocks. The one is the dense blocks and the other is the transition blocks, and also have with some different functions. So then we kind of get the synthetic data set to validate the performance of these deep learning models. And as I said, we kind of use the model multi-label classification. So here we kind of create the 6 different labels referring to the different types of disturbances. At the same time, also kind of consider different combinations of the events and with the different level of the noise. And this table means some parameters and hyperparameters we considered in our research, and to kind of try to improve the performance of the model. And also, like, actually, when we kind of submit our paper, we got like a question from the reviewer. They asked me like, why you kind of use this like 3, let's say, when you split this data set based on this standard. And I could say that it depends on your, let's say, data set amount, data set size. In our case, we kind of consider maybe the data set is like including 10,000 data sets. And like this siting could be the best one. And when you have like a more, let's say, bigger data set, then you can also kind of increase the, I mean, the part of the training set to make the performance better. So here is like some experience stuff. And then here is some results of the training data set, also the validation data set. And from this result, we can see that the mobile night had the smallest size regarding the model. The desk net is the smallest regarding the size. And the mobile nets, they are the quickest regarding the running time. And then we'll further just continue the validation on the test data set. And also we show there are some like the results on the different PQ events. And here we can see just like among all the PQ events, the transient is it shows the worst results. I guess it's also kind of reflected in the previous results. We see that from the result of FF, the transient show the most messy, let's say, the results, because they have a really, let's say, a sudden change compared with some other parameters from other disturbances. And overall, the rest nets it's really show really well balanced in terms of both the running time and also the accuracy. So in our further research, I guess we will kind of do some further work based on the ResNet. So then I kind of I could say it's everything from my today's presentation. And in case you have any question, feel free to let me know. And also we will kind of upload our models, our data set, and also our code in the GitHub soon, maybe a few days, hopefully. So in case you are interested, also kind of you can just pay attention to my GitHub. Yeah, and thank you.